Hey everyone, today I'm going to try to make a zero fuel water heater that uses free energy from sources like wind and water to directly create endless hot water. Creating heat is an energy-intensive process, and it usually requires a lot of costly fuel or electricity and is especially challenging in off-grid situations. But I think I've come up with an easy DIY way to eliminate the need for the fuel or electricity. And after the initial cost of the build, it's endless free hot water powered by wind or water. The idea was born a few months ago when I made a video I'll link below of a DIY generator build and explained how magnetic induction works to create electricity from magnets and copper wires. A lot of people asked why I didn't use iron cores in the generator's coils. There are actually a lot of reasons why you might choose to go coreless, and let me know in the comments down below if you want me to do a dedicated video on the pros and cons of cored versus coreless designs in generators and motors. Well, one of the reasons you might avoid cores is that they generate a lot of waste heat that you have to remove from the system. And you guys asking about it got me thinking, instead of treating the heat as unwanted and trying to minimize it, what if I designed a system that maximized the heat created instead and used it directly to heat something like water? So I've designed an axial flux water heater, and here I'm going to go over the science behind it and then build one to see how well it works in practice. If you place steel cores inside the coils of the generator, you'll increase the strength of the magnetic field, or flux, passing through the coils. And that will increase the amount of electricity that the generator is producing. The magnetic field that is passing through the copper coils to create electricity is also passing through the steel cores, inducing free electrons in the iron atoms to move similarly to how they do in the copper. The big difference between the two is that the copper coil is made of a long piece of enameled wire, so the electrons only have a specific direction and path that they can travel in, whereas the cores are just chunks of steel, so the electrons can basically flow in any direction. Now, while they can theoretically flow in any direction, they tend to swirl in little circles that resemble eddies swirling in water, so they're called eddy currents. So as the magnet passes the core, you get swirling loops of electrons that aren't doing anything beneficial like creating electricity, but the movement of all the electrons is creating a lot of friction within the steel, and that friction is creating a lot of heat. So this is where I got thinking, what would happen if we optimized the build to create eddy currents instead of trying to minimize them? Because it's a potentially really good source of heat. This isn't a new concept. It's used in things like electromagnetic braking. I've just never seen it used in DIY water heating. Creating heat usually requires a lot of fuel or electricity, but it's really easy to spin a rotor with an alternative energy source like wind or hydro. And this could potentially be a really efficient way of creating heat because it's creating heat directly. We're not first creating electricity and then converting it to heat, which will have a lot of conversion losses every time the energy is converted from one form into another. If we could skip the electrical process entirely, but use the same wind turbine to create eddy currents intentionally, we could probably convert more of the rotational energy into hot water. Then, not only have we increased the amount of hot water we get, we've also eliminated all the most costly and complex parts of the electrical system. I think this idea has real promise, and it's definitely worth playing with. And I've already built an axial flux permanent magnet generator, so I think it should be really easy to keep the magnetic rotors in that build, but just swap out the stator for one that's built to optimize for eddy current production and that you can also pump water through to extract the heat. So because the magnetic field lines are pointing straight from one rotor to the other, we want a flat disc as a stator in between the two rotors. Next, we need to be able to pump water through the stator to extract the heat. So I'm going to try using copper tubing wound in a big coil that can act as the disc. Copper is an ideal material for creating eddy currents. It'll be easy to pump the water through the copper tubing, and it has great thermal transfer properties, so the heat will easily transfer from the copper to the water. Now, because we know the eddy currents flow in this plane, I want to eliminate any of the gaps between the turns in the coil. So I'm going to solder the entire coil so it becomes a single solid disc. This should help the eddy currents flow so we get more heating. So that's the basic plan. Now let's start the build. To make the copper coil, I'll start by making a jig, and I'll sketch it out on the table to get the shape and dimensions correct. So this is the band where I need the copper pipe, and this is just a spot to avoid because the axle will need to run through there. So I need to make a jig for this circle to wrap the copper pipe around. So if I make these two shapes as the jig, then the copper pipe can snake through the middle here and both ends can wind their way out. I'll bend the jig shapes out of square bar and make sure they're nice and flat. Then I'll cut the ends and weld them together. Now I'll make the frame that keeps the tubing in a single plane. And I'll weld the center shapes onto the frames. And then drill some holes so the two frame pieces can bolt together. Please remember, likes and subscribes really help the channel grow so we can keep the content coming, and the best way to support us is directly over on Patreon. Now that I've got the jig finished, I can wind the copper coil, and I'll just be using this 8mm copper tubing, and the first thing I'll do is get it straightened out. And this does take a bit of space to get it started, so I'm here in my wood workshop, but I could also just do this outside. And next, I'll go ahead and measure the halfway point of the copper tubing. Then I'll bring the jig over to that middle point, and then I can line up the copper down the center of the jig. Then I'll put the top on the jig and bolt it down. Then it'll be easier if I get both ends of the copper on one side. So I'll clamp this down and just walk this end of the copper over to the same side as the other. So with both ends over there, now I can easily start winding the tubing onto the jig. Then it's really important to keep the coils really tight and touching the whole way out. Okay, so I've got enough coils wound on here. So now what I want to do is just throw a clamp on it so that it can't unwind. I'll go through and make sure all the seams are nice and tight so that it can be soldered well. And then I'll start soldering in the gaps between here. That will lock it all in together. Then I can take the jig off and finish up the soldering. Now I'll cut the tails off and demount it from the jig. Now I'll just clean it up a little bit and then solder in these gaps. And to maximize the eddy currents, I need to solder both sides. So now I'll just give it a quick wash in soap and water just to get any of the last bits of flux off because it's corrosive, and then I'll take it back over to the metal shop and get it mounted. All right, the coil's ready to go, but I need to mount this in a square frame so that I can install it on the generator body. And to do that, I'll just use some copper pipe because it will solder on really easily, and I'll just cut the right lengths to make a square around it, and then I'll hammer this flat enough so that it's the same thickness as the coil. That way it won't interfere with the rotors, and it should be pretty easy to install. And I've got this piece of steel which is the same thickness as the coil, so I can use this as a kiss block to get this thickness correct. Then I'll just hammer the ends so that they can overlap and get soldered together. Now I need to cut one of them in half lengthwise, just so that once it's soldered onto here, it'll still fit in the existing frame. If the frame was a little bit bigger, I could skip this part and just make a fourth one. And now I'll just hammer the seams closed. Now I'll take the original generator apart to install the new stator. So now I'll just drop in the new stator. I'll just use some bearings to mount the whole system to the frame. Just put some thrust bearings on the side and then some lock nuts to hold the thing exactly in alignment. Okay, the rotors are locked in, so now I can line up the copper stator, and I just have these little brackets here. And I can push one to each side, and then I can slide these nuts in and out to move the brackets and shift this so that the copper stays in the center. So now the stator is centered and locked in. All right, we're just about ready to test it for heating water, but I just want to show you one thing that's some pretty cool physics. So the rotors should spin freely, and when it's set up as a generator with coils, they do spin freely. You can just give it one push and they'll continue spinning. But there's so much resistance in this. It comes to a stop right away. And that's actually the friction that is going to be creating the heat that we want. But to explain why there's resistance to spinning, but no physical contact, I can do a demonstration right here. I've got a piece of aluminum here, and here's a piece of steel. And they're not attracted to each other in any way. So if I tilt the aluminum back at a slight angle and drop the steel down it just falls pretty quickly. If I use a magnet instead, it's also not attracted to the steel, but if I drop it, it slides down really slowly. So here they are next to each other. And what's actually happening there is that the magnet is creating eddy currents in the aluminum, just like we're doing here. But the eddy currents are electrons flowing in little circles, so they're electrical circuits. And those electrical circuits are also creating their own magnetic fields that are opposing the magnetic fields of this. So as this slides down, there's a magnetic field right in front of it that is opposing it, and there's a magnetic field right behind it that is pulling it backwards. So it just slides down really slowly. So anyway, I'm just gonna bend these copper pipes, and then I'll clamp this down to the table. So here's just a test bucket of water. Got some tubing and a pump. I'll just connect the tubing up to one end, and then hopefully we can just get this water to spill right back in the bucket. So I'll just plug that in and test the pump out. All right, that's great. So now I'll just set up some thermometers. So this thermometer will be the water bucket temperature. And then this second thermometer, I can hopefully get a reading on the output water right there. All right, that's looking good. So I just need to stick a pulley on this and get this spinning. Now I'll put a matching pulley on the drill here. And there's a bearing at the end so that I can hold it, apply some tension, and drive it with a belt. Okay, there was just so much resistance that the belt kept slipping, so I'm going to take the pulleys off and just go direct drive. All right, it is definitely raising the temperature. Okay, so we've increased the bucket temperature quite a bit, and the outcoming water is getting quite warm. I don't want to burn out the motor on the drill. This isn't a motor designed to run at high torque for long periods of time, but it definitely proved out the system. Okay, so now that we know this actually works, I want to dial in the testing and get a little more precise to find out what this is actually outputting. So I've made a couple changes. The water is exactly 1.5 liters now, so I can track that and track the time it takes to raise it a certain temperature. I've just insulated the bucket a little bit to reduce the heat losses, and I've got a nice fully charged battery, so I'll run it for as long as I can and see how high we can get the temperatures. Okay, so we're starting out at 7.9 Celsius in the bucket and coming out here, so let's start a timer and let's go. All right, that drill is starting to really not like that. But we got up to 28.4 degrees coming out. That's really warm. It's even starting to steam coming out, and the copper will still be warm for a little while, so we're still getting nice warm water out of there. Okay, so that was great, and it proved out the DIY copper coil for induction heating of water. The test ran for 3 minutes, and then the drill motor started to overheat, so I ended it there. But in 3 minutes, it raised the 1.5 liters of water from 7.9 C or 46 Fahrenheit to 24.4 C or 76 Fahrenheit. And the outlet water peaked at 28.4 C or 83 degrees Fahrenheit. So this means, as it was a 575 watt water heater. But this was only at about 400 RPM. And here's something that's really cool. The induced eddy currents scale linearly with the speed of rotation, but the heating power actually scales quadratically. So if we could get up to 1,000 RPM, we'd go all the way up to a 3.5 kilowatt system. And if we could get up to 2,000 RPM, we'd go somewhere to around 14.5 kilowatts. So the system has the potential to create a ton of heat. At some point we'd reach the actual mechanical breaking point, but at 400 RPM everything looked perfect. The copper stator was staying at right about the same temperature as the water, so this means that the water was really efficiently extracting the heat from the system. Next, I'll try hooking this up to a stronger power supply so I can see how high I can really push the system, and I'll also hook it up to a wind or water turbine to test it as a standalone self-powered off-grid water heater. If you enjoyed the video and you want a little bit more detail, we've made an info pack that includes things like material lists and dimensions, and that's available for a few bucks that'll help fund making more videos, and that'll be linked in the description, and thanks for the support. And last, I want to give a shout out to Daniel and B-Shift at Milton Fire Station 44, and to all the firefighters, paramedics, and first responders out there. We're endlessly grateful for all your courage and hard work, so thanks very much, and take care of yourselves. So that's it for this one. I hope you enjoyed it. I'll be back soon with a follow-up on this and a bunch of other videos I'm working on. So until then, thanks for watching.